Hi, this is the Science Chef. In this video, we'll be looking at the second part of a series on chemical combination, covalent bonding and properties of covalent compounds. If you are yet to watch the first part of this series on ionic bonding, you can click on the link in the description to watch it. So go nowhere, as we'll be right back after this timeout. Welcome back. The type of bond formed between two atoms depends on the difference in the electronegativity values between the two atoms. Electronegativity is the tendency for an atom to attract electrons to itself. Non-metals have high electronegativity values, while metals possess low electronegativity values. A metal has about 1 to 3 outermost electrons, while a non-metal has about 4 to 8 outermost electrons. The higher the difference in electronegativity values, the more ionic the bond, and the lower the difference in the electronegativity values, the more covalent the bond. Covalent bonding is a type of chemical combination that occurs between two or more non-metallic atoms through the sharing of valence electrons and overlapping of the orbitals of the participating atoms. There are two types of covalent bonding: ordinary covalent and coordinate covalent or dative bonding. While the ordinary covalent bonding involves the sharing of equal number of valence electrons, in dative bonding, the electron pair shared is donated by only one of the participating atoms. Let's see how ordinary covalent bonding occurs by looking at the formation of single, double, and triple covalent bonds in chlorine, oxygen, and nitrogen molecules respectively, and the formation of water and ammonia molecules. In the formation of a chlorine molecule, two chlorine atoms, each with the electronic configuration 287, combine by sharing one of their valence electrons because they each need one electron to complete their outermost shells. The two electrons used in bonding are called a shared pair or bonding electrons, and the bond formed is called a single covalent bond. The valence electrons not involved in bonding are called non-bonding or lone pairs of electrons. There are 6 lone pairs and 1 shared pair of electrons in a chlorine molecule. To form an oxygen molecule, 2 oxygen atoms, each with an electronic configuration of 2,6, combine by sharing 2 valence electrons because each atom needs 2 electrons to complete its outermost shell. The 4 bonding electrons form a double covalent bond. Therefore, an oxygen molecule has 2 bonding or shared pairs of electrons and 4 non-bonding or lone pairs of electrons. In a nitrogen molecule, 2 nitrogen atoms, each with 5 electrons in its valence shell, needs 3 electrons to attain the octet configuration. Each atom contributes 3 electrons to the bonding partnership, thereby forming a triple covalent bond made up of 6 bonding electrons. Therefore, a nitrogen molecule has 3 bonding or shared pairs of electrons and 2 non-bonding or lone pairs of electrons. In the formation of ammonia, a nitrogen atom combines with 3 hydrogen atoms. The nitrogen atom needs 3 electrons to attain the octet structure of 2,8, while each hydrogen atom needs 1 electron to attain the duplet configuration. So they use each of their lone electrons to form single covalent bonds with nitrogen. Consequently, the ammonia molecule has 3 bonding or shared pairs of electrons and 1 non-bonding or lone pair of electrons. To form a water molecule, oxygen combines with 2 hydrogen atoms. The oxygen atom uses 2 of its valence electrons to form single covalent bonds with the hydrogen atoms, thereby attaining the octet configuration, and the hydrogen atoms a duplet configuration. Hence, the water molecule has 2 bonding or shared pairs of electrons and 2 non-bonding or lone pairs of electrons. Now let's look at what happens when the shared pair of electrons is contributed by only one of the participating atoms by studying the formations of oxonium and ammonium ions. Dative bonding occurs between a molecule or species that possesses a lone pair of electrons and an ion that can accept a lone pair of electrons. In the formation of oxonium ion, a water molecule with 2 lone pairs of electrons on the oxygen atom combines with the hydrogen ion, also called a proton, because it contains no electron nor neutron. So the water molecule uses one of its lone pairs of electrons to form a coordinate or dative bond with the hydrogen ion. The positive charge of the hydrogen ion is transferred to the oxonium ion. At the end, there is 1 lone pair of electrons and 3 shared pairs of electrons in the oxonium ion, out of which 2 are single covalent bonds between oxygen and 2 hydrogen atoms, and 1 is a dative bond between oxygen and the 3rd hydrogen atom. This bond is represented in the oxonium structure by an arrow pointing away from oxygen to hydrogen to show that the bonding pair of electrons was solely donated by the oxygen atom. To form an ammonium ion, an ammonia molecule with a lone pair of electrons combines with a proton. It uses its lone pair of electrons to form a dative bond with the hydrogen ion, and the positive charge of the ion transferred to the ammonium ion. Consequently, the resulting ion has 4 shared pairs of electrons with no lone pair. Of the 4 pairs of bonding electrons, 3 are covalent bonds, while 1 is a dative bond. Next is the properties of covalent compounds. Covalent compounds held together by weak van der Waals forces. Low amount of energy is needed to break those intermolecular forces of attraction. Hence, they have low melting and boiling points. Due to their weak intermolecular forces, the molecules of covalent compounds are loosely held together. Hence, most covalent compounds exist as liquids and gases at room temperature. They do not dissolve in polar solvents like water, but are soluble in non-polar solvents like ether, toluene, benzene, etc. This is because covalent compounds lack ions that can interact with the polar ends of water. This non-availability of ions is responsible for their inability to conduct electricity in solution or molten state. Hence, they are regarded as non-electrolytes. In our next tutorial video, we'll be looking at the VSEPR theory and how it can be used to determine the molecular geometry. Ensure to keep a date. If you enjoyed this lesson, like, share this video, leave your comments and follow us on our social media platforms. Thanks for watching and always stay safe.